Okay, so this afternoon I will be doing a presentation I did in my previous lab about Thrust, which, as Benjamin said, is a library that uses CUDA, and it's mostly it's higher level than what you've seen previously, but it's still based on NVIDIA and can do many sort of things we will see through this presentation. So I'll be first diving into code and presenting you a class that is interesting in this library, which is the device vector that somehow mimics the behavior of the standard library C++ std vector. We'll talk a bit about the asynchronous way to use this library, as we have seen on this morning with Ben. Then we'll see that Thrust, being high level, allows to use a different backend, GPU backend with CUDA, but also CPU backend for some operations. Then the remaining part will be about some practical example of use, and you may be able to find the code on GitHub. Okay, so first, what is Thrust? Thrust is a template-only library, so it's a bunch of files. There is no binary that you can find if you have the CUDA toolkit installed on your computer. It's simply in the include, so you find this Thrust template-only library. So it's, I would say, lightweight because you only have to have the include, and plus the include are always packaged with the CUDA toolkit. So as it's mainly metaprogramming, template-based only, don't be afraid if, when the first time you compile an example, you get like 1, 2, 3 pages of that kind of errors. Just look at the last line, and probably you will be able to find what this doesn't work. But yeah, people that uses template metaprogramming with a lot of template composition are used to it. But okay, so don't be afraid by that. So the device vector class, what is it? It's a container in the same sense as the STL container you may know if you use C++. It's useful to wrap CUDA buffers. We'll see that when I say CUDA buffers, it could be CUDA allocated with different allocator, like you could use pinned memory or managed memory. It's up to you. It's kind of an equivalent of the std vector. What can you do with that? Thrust, along with this device vector class, also provide a lot of algorithm, the same kind of algorithm that you find in the STL when you include algorithm, plus other, like some that are in numeric. It allows you to automate the allocation and destruction process, so you don't have to call explicitly CUDA-free, for instance. It features some error handling mechanism. It's not perfect, but okay, you have some error handling capabilities we will see after. It is host-to-device copy management, somehow in a way that Sam managed to do with its wrapper you've seen already. What it can do for people, for instance, that have already used texture for signal processing, for instance, 2D or 3D textures, or surfaces, which is an API given by CUDA that allows to perform, I would say, fast read-only lookups. So you won't be able to use that through through the device vector from thrust. And as it's designed to be fast, you have no bound checking. For instance, people that uses the the std vector .at with bound checking, you can do that easily with thrust. Okay. A very simple code that is really simple to analyze. What you can do, what would you write a code that do something interesting using thrust? First, you will be interested in declare. So you declare a device vector and a host vector, one residing in a GPU memory and one residing on host memory. Then you allocate or resize. It's the exact same meaning that the STL vector. You can explicitly copy the memory from the host to the device with the iterator semantic. You launch some computation on the device, for instance here, and you can perform an inclusive scan, which is included in thrust, an algorithm included in thrust. And then you copy back to host the result with an explicit copy. This is a very simple code, but looks more C++ than pure CUDA code. Okay, in practice you can have better expressivity. Okay, if you already know the syntax for declaring and performing allocation with the constructor, it's the same as in std vector. Okay, when you've done that on the device, on your device vector, you don't even need a host vector and perform explicitly copy, so that you can perform the inclusive scan directly on the device vector. But if you don't allocate the host vector, you will have to find a way to get the values back to the host. And it's interesting because in this case, suppose that we only want 1 or 2 value from the inclusive scan. We won't be interested in getting all the vector back to the host. So we may be interested in dereferencing some of the iterators inside the device vector. And you can dereference an iterator over a device vector from the host. This can be done. This is handled by thrust. So in a few lines of code, you have pretty interesting functionalities. What is interesting is that if you already have another code or you already allocated memory in another part of your application, you can still use thrust. In this case, I give an example where I've already allocated with CUDA malloc some memory in the device. And I can use this wrapper, which is called device pointer, and is a class of thrust. I can wrap this row pointer inside a device pointer and get the exact same semantic of the iterator we had in the previous slide. So in this case, I can use the equivalent of std field with thrust field on this row pointer wrapper, perform my inclusive scan, and then even also dereference with something that should be a device pointer, but I can dereference it whether it has been allocated with here a CUDA managed allocation or a simple CUDA malloc. This is handled by the device pointer wrapper. Okay, the other way now. Imagine that you have your unwritten kernel here that you want to keep, but you want to simplify the memory management using thrust. So you have here your unwritten kernel. It's very naive sequential scan on the device. So you allocate your device vector from trust. You launch asynchronously using streams your naive sequential scan, which is your unwritten kernel, and you pass it the row pointer that can be obtained using row pointer cast. Okay, so whether you had already written CUDA code before, you can use trust in multiple ways. I told you before about error handling. In this case, I've used this, let's say, C++ construction with try block, try catch block. And trust can catch some errors for you, but you have to be careful because you have to remember that if you have error arising in CUDA code on the GPU, as GPU kernels are asynchronous with respect to the host, if there is an error, you only will be able to catch them with the synchronization API from CUDA. So here it's an example, but you have to be really careful. There is no synchronization here. You won't be able to catch error that arise in the device during the inclusive scan. Those errors are mainly intended to catch like allocation errors or destruction errors or things like that. But at least it allows you to have to set up a proper error handling mechanism. Okay, this is linked with what Ben presented this morning, the asynchronous, the fact that you can use asynchronous call through this library, which is not that old. I think it was set up 1 or 2 years ago. Okay, you already have seen that using CUDA as an asynchronous library is interesting because you can set up the compute copy, have overlap between compute and copy, use the streams you've seen this morning, and Thrust actually extends the semantic of streams by providing a more general things called the execution policy. We will see just after. But you have, as always, when you use asynchronous API, you have to be aware that there could be problems. There are some things that that won't work, that won't allows you to use asynchronous API properly. Like if you use pageable memory, sometimes you won't be able to parallelize a copy on compute, for instance. As always, if you divide your workloads into chunks, you have to be careful and about the size of the chunks to be sure that you'll in practice will get acceleration from dividing your data. Don't use the default stream. Allocate your own streams if you want to use the asynchronous library, and be careful about the copy and gyro source of the GPU you're using. I'll get back to that later. Okay, what is an execution policy? Thrust as a concept of execution policy that allows you, when you have a specific operation, for instance, the inclusive scan we've seen earlier, to launch it whether explicitly on the host, on the device, to launch it sequentially, which could be interesting, for instance, if you are debugging and that you have an associative operator, but if you want to have the same result every time, you have to compute the operation in order. This can be also used from the GPU, because from the GPU you often don't want to launch new kernel. So if you want to to launch say a loop inside the GPU code, you can use this execution policy. You can use OpenMP. That means that if you have a GPU you you want to perform the inclusive scan on it, you use this execution policy, but you can use the OpenMP, or another one that I will be talking about after, which is thread building block, a parallelization library, originally designed by guys from Intel, I think. And finally, you are able to provide an execution policy which is asynchronous through the use of stream you may have declared earlier. For people that knows about C++ 17, it's exactly, this concept is exactly the same that the one that you can find under execution policy tag in C++ 17, where, yes, I took examples from the C++ 17 syntax. In C++ 17, you will be able to mimic the behavior of thrust with the STL algorithms. Okay, so this should ring a bells for you. You've seen this morning with Ben that dividing data in chunks is interesting when you have let's say when you have a computational burden that is similar to the time used for copy. Here I'll present, okay, this is not really nice, but I'll explain you. I'll present two solutions to use streams and asynchronous library to, let's say, to exploit the GPU and its copy engine at their best. One solution consists in allocating a vector containing, let's say, n, an arbitrary number of streams. And we will be designing only one loop here. It's important to notice that there is only one loop. And if we divided our let's say, our data into data chunks, which I call strip here, we will be able to, for each chunk, to launch sequentially those operations, first synchronizing to ensure that we won't be modifying a buffer that is currently used by the previous launch. Then copying to device, copying the memory to device, so using CUDA memcopy asynchronous with the stream here. The computation, here it's a stress transform. And copying back to us, still using asynchronous API with the stream everywhere, here also. Okay, so we can do that in only one loop, but there is also another solution, which is for each operation, do one loop. So perform the synchronization over all previous work, then launch all the copy from host to device, and launch all the, let's say, workloads, and then launch all the copy back to host. This is another solution. Both should work. But in practice, when we tested those two solutions and used the NVIDIA Visual Profiler, we got two very different profiles. One which is absolutely not interesting, because we can see here that all operations have been launched sequentially, and one which is a bit better, but as you can see here, there are copy and compute, copy and compute, copy and compute, but the copy back here arises only after, but I'll talk about that later. Can you guess from the two solutions I presented here, the one with only one loop and the second with 1, 2, 3, 4 loop, which is which? This is actually difficult. Okay, I'll tell you the solution. Actually, the red here, the red one corresponds to the one with only one loop. And you may ask, okay, but why is there a synchronization between the end of the copy from device to host from the first stream and the copy from host to device on the second stream? Although here, when it's expressed, as everything is launched in a different stream, yes, each each of the elements of the loop have been launched in a different stream, they should be launched in parallel. But what arises if you use a card, for instance, from the GeForce series, is that you have actually only one copy engine. What it means is that when you launch a copy, whether it's from host to device or device to host, those copies, even if they are asynchronous, are pushed inside a queue, and a copy engine can be seen as a queue. And if you launch sequentially a copy from multiple copies, this copy will be seen by the copy engine as a task in a queue, and it has to finish one task before beginning the other. So here, the single copy engine of the GeForce card I used for this example, which was a GTX 680, has sequentialized the copy from host to device and the copy from device to host and the next copy from host to device. This is why, in this case, it was more interesting to use this pattern so that all the copy from device to host, from host to device, are launched and seen by the copy engine before the return copy. So anyway, here you have to think about the copy engine. And here, all copy from host to device have been launched in the right order. But as you have only one copy engine, anyway, you won't be able to perform a copy from device to host in the meantime as a copy from host to device. So this is why here you're still losing time. But when you use a Tesla card and you have a double copy engine, you don't have to care about that. But I'm telling that for people that use GeForce series card. Okay, now I'll talk about the versatility of Thrust, the fact that it's able to perform computation on both backends, CPU or GPU. Okay, it's basically interesting because you can code only once and get multiple implementation, don't have to rewrite the code. And it's also interesting because if you want to give an idea of the GPU speed up, it's really easy to do with Thrust. Okay, first a really simple introduction. Most of you probably knows about OpenMP, Open Multiprocessing. It allows to perform parallel programming by simply adding a preprocessor directive. And it's automatic. It means the compiler is doing most of the thing for you. But it also features a really interesting complex directive, like with OpenMP 4.0. It's really interesting to look at that. A very simple example. Okay, I want to parallelize this loop. Just parallelize this loop. Okay, this was the introduction for OpenMP. TBB for thread building block is a really interesting library. Some of you may know. This book is really interesting if you ever had time to look at it. Even if you don't intend to use the TBB library, it explains a concept of parallelism in a very, very clever way. So it's a C++ library that features work stealing, but many other interesting features for parallel programming, mainly in the form of algorithmic skeletons. So it's not preprocessing directive like in OpenMP. It also features really interesting containers that you may be interested in if you have to, for instance, push in a single queue when you have a lot of threads, hash map that are thread safe, and etc. Okay, many interesting things. I won't tell much about that, but it's just interesting to know that Thrust has a TBB backend, so you can compile your code for OpenMP or TBB backend. Okay, this was just an example of thread building block, but I won't talk much about it. So here I've already talked about the execution policy a few slides before, but you don't have to use the execution policy explicitly if you want to parallelize your work. You can specify the backend system at compile time using, for instance, one of those three backend, CUDA, OpenMP, or TBB. And so, for instance, yes, the name of the variable is trust device system. And for instance, in my case, I just put that in my CMake list. And by providing this variable to the compiler, you can have a multiple backend. So it's just only compile time decision. Okay, there I did very simple example for the sorting operation. And with a timer here, and I was doing a sort with iterators I've seen previously. Okay, the only difference when you're using the various backend is that you're still it's still required to use CUDA device synchronize when you use the CUDA backend, because otherwise, as CUDA is all the time asynchronous library, you won't be able to perform proper timing. So okay, so just one line which should be explicitly stated if you want to use the trust device system CUDA. But otherwise here, the trust sort is the same, and I don't have to specify here an execution policy. So I run this code with the three different backends. And I got those results in terms of millions of elements sorted by second. I think it was on a GTX 680, and the processor was an i7 3870, something like that. And yes, with a single, I would say with a few lines of code, I was able to perform a speed-up calculation. So okay, maybe you won't be interested specifically by this aspect, but it can be interesting in sometimes. Okay, now I'll switch to very practical examples that I've used. Here it's a very simple convex optimization, like gradient descent, based on trust and cuBLAS. Why it can be interesting to use trust. This talk was initially mainly for people that used C++, but that had not a lot of time to invest in learning CUDA. So if you have a lot of iteration, of course, it's interesting to have a short time per iteration, which is sometimes the case where the problems are ill-posed, and you have to use iterative methods. And of course, if the problems are very large, it's interesting. Okay, so in this example, my intent was to simply solve a least square, very simple problem, with A being a linear system. And here in this case, the product A times X will be performed using cuBLAS when I'll select the CUDA backend, and to implementation of BLAS on the CPU when using a CPU backend. Okay, and so it's just a gradient descent, really simple algorithm. So what is cuBLAS? Ben already talked about it. So it's a highly optimized implementation of the basic linear algebra strip program made by NVIDIA. So what was my strategy while implementing this simple algorithm? I actually wrapped everything inside a higher-level interface, so that I would be able to use for instance, a matrix vector multiplication, whether through BLAS or cuBLAS. So I did a wrapper kind of interface for that. Yes, I wrapped the cuBLAS SGMV inside the product class that I designed. Okay, and my vector was stored in Thrust vector wrapper, also a wrapper that I wrote, but very simple, just a few lines. Okay, and here is what my algorithm look like. So I have my linear system called A, can make a product which under the hood will call cuBLAS if I use the CUDA backend, or BLAS if I use the CPU backend. And I implemented very simple operations, subtraction, product with a transpose matrix, and AXPI. Here I was mainly using single precision, yes. And I was able to run my gradient descent with multiple iterations. What was interesting in this case was to compare the number of iterations I was able to perform in a given amount of time, in 1 second here. And I was able to benchmark. So the CUDA implementation, of course, was the same as the 2Ks. But it was interesting that I was also able to, with the simple wrapper I did, to switch from an OpenMP with the default implementation of the BLAS interface in my computer, which was like, I think there is a libopenBLAS, and I would say the Intel software stack with a thread building block and MKL library. And here it was really easy to compare the speedups and see if it was interesting to use to buy, for instance, a GPU. Another example now, a simple instance of gradient descent for the specific case of signal processing. You may have heard this is something really common in signal processing, which is to exploit gradient sparsity. So when you have an image like that, gradient of the image is actually a vector field, which have 2 values for each point, values in X and values in Y, of course. And it has been a very famous model called total variation, exploit the fact that natural images always feature mainly zeros, but a few non-zeros term when you compute the norm of the gradient in each part. Okay, it's a very simple approach that is often used in signal processing. Out of that, you can design a convex objective with a data fitting term here and a regularization term here. This regularization term being related to the L1 norm of this image. And okay, I'll skip that. It's just to explain how we transform this this convex objective, which was non-differentiable in blue here, in a differentiable one, but not really serve my purpose here. So we implemented with the kind of the same framework our algorithm, our optimization algorithm. And we implemented that not for 2D images, but in order to keep the problem really simple on 1D signals. I will show you the example just after. And we were even able to compute the gradient in 1 dimension using this nice function from Trust, adjacent difference. And the algorithm, as you see, is really simple. Our aim was to denoise the actually green signal you can see here with the total variation model, and the curve in red is the denoised signal, and the curve in blue you may see under is the original signal. So okay, this algorithm is very simple example of what you can do in signal processing. And here again, with the 3 backend, we compared how many iterations we were able to do with multiple backends. And with this simple example, we were able to see that, okay, if you do 1D signal processing, it's really interesting to use CUDA. At least you can be sure that it's interesting. Okay, now after the example, just a few information you may be interested in. Don't hesitate to look at the official documentation from CUDA, and especially there are 2 things you can be interested in. The programming guide, which is more general on human-readable format documentation with a lot of examples of what you can do and how you can use the CUDA API. And in another directory, there's the CUDA runtime API documentation, which is a real documentation that you may be interested in. When you look for a very specific function. There is also, of course, the Thrust official documentation. If you have problem, you can ask on CUDA official forum, which is interesting when you have very specific problem or performance questions. Stack Overflow, of course. If you want to learn more, there is a good massively online course on Udacity. You may be also interested by the work of Mark Harris, which is a chief technologist at NVIDIA. He has a very nice GitHub with lots of nice examples. And most of the code that has been showed in this presentation is available on my GitHub in CUDA Thrust Introduction. And if you want to be able to just simply compile some example and run it on parallel using Thrust for CUDA and plus MPI, you can use the code which is here for Daint. Okay, so in conclusion, what does Thrust may allows you to do? It allows to save coding time if you are more into, if you're not into optimizing things, which can take a lot of time. It makes the code clear if you are used to high-level concepts from the C++ language. If you are a scientist and that you need to do intensive parameter exploration, it's interesting to use CUDA with a lot of GPUs, of course. And you may be interested in Thrust if you want your code to run both on GPU and on CPU also. Take-home message, I think that Ben already talked about that. Think parallel, use libraries whenever you can, and it's always convenient to use wrappers. Thank you very much. If you have time, I may show you other examples, but right now, if you have questions, don't hesitate to ask me.
Question about the transparent copy of, say, a device vector through to the host 3D iterators. Is that a single transfer every time, or is there some sort of caching that goes on underneath?
Okay, the question was about the transparent copy that I showed at the very beginning. I did not, okay, it's at the beginning. Okay, it's here, for instance, when you, okay, the question was, is there a caching mechanism here to look at the values from the device memory when you are in the host? I don't think so, actually. You should take a look at the device vector implementation. There is probably the implementation of the star operator here, but I don't think that they at its template only that they have used a like one value or few value caching mechanism. I think it's mostly basic. This is not, I won't use that in production, but when you are debugging, for instance, and you don't want to have to write a lot of code, it could be really interesting to use that feature.
Yeah, it's a simple proxy. Okay. So when you dereference it, it's going to call a CUDA mem copy on that single value.
Cool. Thank you.
Yes?
Does Thrust handle multiple GPUs in the server?
Okay, so the question...
Is this asynchronous, just distributing on one of the available ones or things like that?
Okay, so the question was, does Thrust handles multi-GPU? So I'm very happy that you asked about that because I have a bunch of slides about the topic because I did use it for multi-GPU. So first, unfortunately, it doesn't handle multi-GPU settings for you transparently. So if you have multiple GPUs, you will have to do some modification. But I can show you a simple example when I did that, because I had multiple GPU on my computer. Yes. Okay, here, this is actually a good question. Why Trust does not handle that for you? Because actually there are multiple kinds of multi-GPU. Multiple GPU on a single node, for instance, can use for communication a very different pattern depending on the PCI network configuration. So they maybe have peer-to-peer access between GPUs, or it may not. So I think that Trust stays generic and don't assume that you have or don't have GPU peer-to-peer access between GPUs. But you can somehow exploit multi-GPU when you have the unified virtual addressing. So I wrote the slides before the CUDA managed memory support was as good as it is now, because before I would say before a few months ago there was CUDA managed memory and virtual memory, but you were not able, for instance, to do oversubscription, which is something that you can do now, but just until a few months ago. But yeah, this will actually help you to have the single addressing space for multiple GPU. Okay, I'll show you an example. Here in the example I was presenting, I was supposing that I had multiple vectors and one vector of 4 elements on each GPU. On here, okay, 8 GPU, so it's a very beefy node. And I wanted just to perform a reduction over each of the elements of the vector to get only one vector at the end. So you can do multi-GPU programming, but you have first to ensure that each time you will call allocate a device vector, you use the CUDA set device API from CUDA. Every time you will do something with a GPU, you have to ensure that you use the CUDA set device. Okay, here I was only, it's not really interesting, but I was only allocating a device vector. So I was allocating a vector of device vector. And what I've done in this, I was just executing for, I would say, like in a log2 tree, binary tree reduction way, reducing from one vector to the other using this function reduce vector, which was actually under the hood only a transform with the iterator from one GPU on the other GPU with the binary operation plus. So you can, I mean, nearly everything is compatible with doing multi-GPU, but it is not as easy as just using reduction and it all do the things for you, but you can do that. I can maybe just show you I don't know if you people use many, how to say that, features from concept like functional paradigm. Who does know about functional programming here? Few people. Yes. Functional paradigm is interesting. Most of the people that learn first, for instance, C, used to think about sequential and loops and everything. But it's interesting sometimes to think to the problem as with a functional paradigm. Some of you may have heard of MapReduce paradigm, which is really well known since the parallel computing has been accessible from high-level languages through for instance, the Hadoop tools or Spark tools. Here I'll show you very simple examples that arise during my PhD, for instance, and that are related to somehow functional programming. For instance, I had a problem where I had a bunch, actually 8 extremely large, let's say large vectors with like 1 billion elements each. So 1 billion, 8 billion elements here, which were not contiguous. That means that for each element, the starting address was not contiguous with the end address of the previous one. And I had to perform this matrix multiplication, which was arising in a wavelet relating transformation. So I was not able to easily use a, let's say, a BLAS subroutine or a cuBLAS. Plus, even if I was able to use that, it was not that simple to treat the case where there were enough space to put all the data on the GPU, or if I had to compute that on the CPU. So I was also interested in changing the backend depending on the size of the data. So what I did is using the zip iterator. You may have heard of. A zip iterator is simply a way to generate what is called the structure of arrays, SOA, opposed to array of structure. Structure of arrays, Mr. Messner yesterday told about that and said that it was interesting for coalescing memory accesses. But how to generate structure of arrays when you actually have arrays that are at completely different location in your memory? You can do that by zipping actually individual iterator into a zip iterator. In this case, I use the thrust zip iterator with all my beginning iterator of my 8 vectors, the same for the end iterator. And I was able to launch a kind of for loop, which is expressed here in a, let's say, functional way, with a transparent begin iterator and end iterator that was featuring all those individual iterators. And I had to apply this operator, which I'll describe just later. Okay, it's not really interesting, but you just have to know that this kind of operation, where I used well, each output is a linear combination of some of the output. This is actually just an implementation of this multiplication, and I was able to implement this multiplication with this line, and thanks to the zip iterator. This is a functional way to. This is for people that are used to use functional programming. It's interesting. I've also presenting very simple example of functional programming, beginning with a numerical integration example. Some of you may have seen that in some benchmark. It's an example of how to compute pi with actually integrating 1 over 1 plus x squared between 0 and 1. Using the midpoint rule. So one very simple way to do that is to use a for loop and divide the integral into small chunks. Here are 1 billion small chunks, and do a simple loop. Okay, this is a way to write the integration. But thanks to thrust, you can have a more functional view of this loop. Okay, this will not be really easy to understand, but actually what this loop is doing is actually making a transformation over the input data, and here the input data are only the I between 0 and 1 billion. So it makes a transformation and it reduces, it accumulates the results. So you have actually a composition of 2 operators, a transformation operator and a reduction operator. And using thrust, you can perform this operation using a reduce over iterator that are themselves expressed in functions of the input. So here you can use counting iterators to mimic the behavior of the I variable from 0 to 1 billion. And a transformation operator up here, which is just the function 1 over 1 plus x squared multiplied by 4. and you perform the accumulator with the associative operator plus, and this gives you the result. Okay, here it may be a bit difficult to read, but of course you can put the construction of the transform iterator before that. What is interesting about this formulation is that when you use CUDA, sometimes you will have a composition of multiple operators. If you have to, in your code, I mean in your, when you're doing software architecture, if you have to launch multiple kernels, if you are able to do that with streams and everything, that's great. I mean, you don't have to go back to the host, synchronize, and launch again a kernel. But it's bad because in any case, each kernel will have to load the data and write the data before a new kernel is called. Using this solution, what you are doing is actually a composing operator at compile time. So it saves you the cost of every time storing, retrieving the data and storing the data. So you may be, if you want to learn more about that, take a look at, I think it's called Fusion, operator Fusion. Okay, that was what I wanted to say. Thank you. It's useful to wrap CUDA buffers. We'll see that when I say CUDA buffers, it could be CUDA allocated with different allocator, like you could use pinned memory or managed memory. It's up to you. It's kind of an equivalent of the std vector. What can you do with that? Thrust, along with this device vector class, also provide a lot of algorithm, the same kind of algorithm that you find in the STL when you include algorithm, plus other, like some that are in numeric. It allows you to automate the allocation and destruction process, so you don't have to call explicitly CUDA-free, for instance. It features some, I would say, lightweight, because you only have to have the include, and plus the include are always packaged with the CUDA toolkit. So as it's mainly metaprogramming, template-based only, don't be afraid if, like when the first time you compile an example, you get like 1, 2, 3 pages of that kind of errors. Just look at the last line and probably you will be able to find what this doesn't work. But yeah, people that uses template metaprogramming with a lot of template composition are used to it, but okay, so don't be afraid by that. So the device vector class. What is it? It's a container in the sense, in the same sense as the STL container. You may know if you use C++ to use this library, as we have seen on this morning with Ben. Then we'll see that Thrust, being high level, allows to use a different backend, GPU backend with CUDA, but also CPU backend for some operations. Then the remaining part will be about some example, practical example of use, and you may be able to find the code on GitHub. Okay, so first, what is Thrust? Thrust is a template-only library, so it's a bunch of files. There is no binary that you can find if you have the CUDA toolkit installed on your computer. It's simply in the include, so you find this Thrust template-only library. So it's okay. So this afternoon I will be doing a presentation I did in my previous lab about Thrust, which, as Benjamin said, is a library from that uses CUDA. And it's mostly, it's higher level than what you've seen previously. but it's still based on NVIDIA and can do many sort of things. We will see through this presentation. So I'll be first diving into code and presenting you a class that is interesting in this library, which is the device vector that somehow mimics the behavior of the standard library C++ std vector. We'll talk a bit about the asynchronous wait error handling mechanism. It's not perfect, but okay, you have some error handling capabilities. We will see after. It is host-to-device copy management, somehow in a way that Sam managed to do with its wrapper you've seen already. What it can do for people, for instance, that have already used texture for signal processing, for instance, 2D or 3D textures, or surfaces, which is an API given by CUDA that allows to perform, I would say, fast read-only lookups. So you won't be able to use that through the device vector from Thrust. And as it's designed to be fast,